So, this is my air compressor, and this is my pressure cannon. What will happen is that I will load this ball into that chamber, which is approximately 3 inches in diameter. This is like around 2. And this is a sprinkler valve actuated by a diaphragm that I've modified to release pressure really quickly via the mechanism. This is the pressure ballast. And this is the pressure gauge, which has a precision of around plus or minus 3 psi. This is my brass nipple, and this is where I will connect my tangled air compressor to, like so, and giving the tool some pressure. I will now allow this to build up, and that will probably start kicking up. And before it does, load the ball into the chamber and pull the mechanism and fire. So this is the method I'm getting my data. First, the firing mechanism at around 75 psi plus or minus 3 psi. I will be videoing my little brother's stopwatch, and I will be videotaping that using super slow motion, and I will take the time at the start position minus the time at the end position, which will be set at 1 foot, and I will get feet per second after dividing those values, and I will put them in an Excel sheet. I'll perform this about 15 times and perform regression analysis and statistical analysis, hypothesis testing, all that kind of good stuff. Now, as you just saw, the phone stopwatch was actually considered obsolete because it didn't have enough resolution and refresh rate to capture the amount of time it took to traverse 1 foot in the video with super slow motion. However, we can count the frames that it takes to reach 1 foot between the starting position and the end position. We know that this phone camera for a Galaxy S10 shoots 960 frames per second for super slow motion. If, for example, the ball took 8 frames to travel 1 foot, we can calculate how many seconds it took to traverse 1 foot with this formula here, and find the exit velocity by dividing the distance of 1 foot divided by the time, and we get a nice pretty number of 120 feet per second. So as you just saw, we are going to apply all of that to Excel. So where we see 30, 35, 40, 45, these are all pressures, PSI, which were tested. And these were the amount of frames it took the ball to traverse 1 foot. And these are amount of seconds using the formula previously shown. And this is the exit velocity that was calculated. Now, if you'll notice, here's the velocity versus pressure. There is quite a strong relationship, and you can clearly tell that there is a relationship between the amount of pressure in the ballast or launch pressure and the exit velocity. So as launch pressure increases, exit velocity also increases. Now, if you direct your attention to where my cursor is right here, we have a mean of 70.8 feet per second and a standard deviation of 33.5. That is quite a spread of data, but however, we are not testing the frequency of data. We are testing the correlation between launch pressure and exit velocity. Now, with that in mind, we cannot perform hypothesis testing as well as anything to do with testing a null hypothesis, because we would need at least 30 separate experiments with their own values to test the frequency of which they occur for a specific pressure. And then we'd be able to test a null hypothesis. Well, there is no effect if so-and-so happens, and then we can test with a 95% confidence. The only thing we can know with a 95% confidence is the correlation, which was calculated here with the student T distribution. And since we have a 0.98 correlation, R value, RXY, since that is greater than RT, we know that there is a strong trend between launch pressure and exit velocity with a 95% confidence interval, because we use 0.05 for the value in the RT. Furthermore, there are no outliers. Data point 9, which is this point right here, we know that that point is the furthest away. And since this value is less than 2, we know that for all the others, there are no outliers. 18% was the calculated highest uncertainty for each measurement, which is actually quite high considering all of the resolution and precision of the instruments. And as mentioned earlier, this stuff ball 2 inches and a sprinkler valve were used. Oh, my apologies. So as for this specific experiment, since there was not sufficient data for a proper probability density function, we cannot reject or accept a null hypothesis. The reason behind this is that the procedure is derivative upon a PDF that is similar to a Gaussian curve, and this is not a Gaussian curve. This is maybe 1 or 2 values per bin, 4 at the extreme. As for Taguchi arrays, since there are no parameters other than the launch pressure that were tested, we cannot create a design array simply because there are no other parameters to be tested when investigating the correlation between launch pressure and exit velocity. However, if there were data on the internet related to this, I would have looked it up and performed those tests on it, but since I did it myself, I do not have that data. So my apologies for that. We'll take whatever consequences follow, but thank you for listening.